Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at reactor design for our Design 1 class based on the textbook by Turton et al. So we are ready to now talk about equilibrium. We've talked about conversion and yield, selectivity, those kinds of things. But now then, the thermodynamics is going to determine our equilibrium. And we're not going to be able to go past that without changing the conditions of our reaction. So all reactions are reversible, but some, are barely reversible. But we always need to consider the equilibrium. So the equilibrium constant is the product of the compositions to the stoichiometric coefficient power of all of our products multiplied together divided by all of our reactants multiplied together. And those determine the equilibrium constant. Now, this is a strong function of temperature. You're going to need to solve this for what your outlet composition is. And it might give you multiple numerical solutions possible. But typically you're going to get these and only one of them is going to be physically realizable. Remember that this has to be, a mole fraction has to be between 0 and 1. Now if you change the temperature or you change compositions or if you change the pressures, all of those values will change. So it's going to change your equilibrium. So if you don't like the number, look at what would happen if you modified these other conditions. So an example again from back in the material balance course is we have a simple reaction here where the actual chemicals are renamed as A, B, C, and D for simplicity. And if we have an equimolar feed of A and B, what reaction product do we get if we go to equilibrium with an equilibrium constant of 4.87? And so all you need to do is write the expression out for equilibrium constant and then algebraically solve this for the extent of reaction. And in this particular case, we get two answers, 0.9143 and 0.3441. Now, when you look at that, you're like, wait a minute, you said there would be one that was going to be between 0 and 1. Well, remember, you need to take these and plug them into the mass balances or mole balances. So look for X for A, B, C, and D at the product. And 0.9143 gives negative values there. So that's how you can determine which is possible or impossible. So when you're doing this, a lot of the reactions are going to appear to be irreversible. So, oxidation reactions are a kind of well-known case of they just don't really seem to be very reversible. If you have something that rusts, you're not going to sit there and say, well, if I wait long enough, it will unrust. Okay? But because reactions are reversible, it doesn't mean that they are actually going to get to equilibrium. And so reversible reactions are going to be limited by equilibrium, but not necessarily get there. Okay? If you get to equilibrium, then you get to apply Le Chatelier's principle. Now, kinetics is our other issue. So we've talked about selectivity and conversion. We've now talked about equilibrium. Conversion or kinetics is our final way of describing our reactions. And we're going to absolutely have to have this information in order to complete our design. Now, typically a rate of reaction is going to be of the form that the rate of disappearance of J is going to be K times the product of the concentrations of various components to various powers. Okay? And that K is going to typically vary with temperature according to the Arrhenius equation. So the exponential of -1 over T times E over R. R is the gas constant and E is an activation energy. For an elementary reaction, it will take that form. So, like the rate of disappearance of A is K1 times CA to the N power, CB to the M power. And when you have just a nice homogeneous reaction in a single phase, frequently this is going to be what you get. When we have those solid catalyzed reactions, which are incredibly common, and other models are more prevalent, and the Langmuir-Hinshelwood kinetics equation is the most frequently encountered. And it takes a form where you have something that looks like the elementary reaction in the numerator, but it's 1 plus a sum of those sorts of terms in the denominator. And this is going to make the mathematical solution a little more complex. But again, remember, we're going to be taking these into a simulation, and the simulation will handle the more complex mathematics. So this concludes this set of lessons. We're going to next be moving into the details of how you select your reactor scheme. Thank you very much for your time.